Very good morning to all. Today lecture is deal with the in the in the relationship between the resistive, capacitive, and inductor. Okay, so the current voltage in the pure resistor circuit. And relationship between the voltage and current in the pure resistor circuit, pure inductive circuit, pure capacitor. As well as we'll know about the RL circuit. So RL series circuit, RC series circuit, RLC series. So what are the characteristics of these circuits? So how it will be the problems will come. So how we have to find out the problems. Voltage and current characteristics of the in RL circuit, RC circuit, RLC circuit. So first we'll discuss about the we have already discussed. Just we'll go to the recap of the R. So that is a resistive circuit. So relationship between the voltage and current in the pure resistive circuit. So here we are having the pure resistor diagram is nothing but so AC through the pure resistor. So pure resistor is nothing but doesn't have having any losses. So with the resistance opposing also there is no loss. That is a pure resistive network. So here having the AC power supply and here the resistor and current is flowing through this one. So here there is no losses in this one. That's called as the pure resistive network. So here let me applied voltage. So applied voltage is taken the V is equal to Vm sin theta. So why we are taking the Vm sin theta? That is that we have discussed in the previous. That is a Vm, that is the mod. Mean voltage, and the sin theta. The angle. So and for sin representation, that is Vm sin. So V maximum sin theta. So here we are taking the that is a sin omega t. So theta is equal to omega t. That is the value will be changed with the account to theta value. Angle. So Vm sin omega theta, that is equal to Vm sin omega t. Equation 1 we are considering. So R is the ohmic resistance. That is the resistance in ohms. And here is the I is the instantaneous current. So we already know about the instantaneous current. So instantaneous current is nothing but is the if it take any this side. So this is the one instant. Here is the current at the point. This is the one instant. Next, voltage drop. So ohmic drop is equal to V is equal to I. The drop across the resistor. So here I have taken the resistor, right? The drop across this resistor, the voltage drop, that is will call the V is equal to IR. So that is the resistor voltage across resistor. The voltage is that is the V is equal to IR according to the Ohm's. So here is the equation 1, equation 2. So here we are taking the keeping the value. So we are substituting the that is the equation 1 value. So we are getting the value. So V is equal to Vm sin omega t. So that is equal to V is equal to I. And I is equal to Vm sin omega t. That is we are taking the I unit. So V by I, right? So then from that one we'll get the Vm. So when sin omega t is equal to 1, add this equation. You can see. So add this equation, if we get this omega t, if it is equal to 1, then it will be Vm by R. So here I is the maximum current when sin omega t. So here we have taken the the instantaneous current, right? So here is the I is the instant. So if at what point is the maximum? There is a when sin omega t is equal to 1. The I current is maximum when sin omega t is equal to 1. And the maximum current Im is equal to Vm by R. So the maximum current at this side is a Vm by R. So substituting the equation. So from that one we getting the I is equal to Im sin omega t. So Im is nothing maximum current. So here we get V is equal to Vm sin omega t, I is equal to Im sin omega t. For pure resistor circuit, the V is equal to Vm sin omega t, I is equal to Im sin omega t. So here if we take a vector representation, we can observe. So V at Ri. So here is the current. So current through the resistor. This one is through the voltage across the resistor. So here is the omega t value. Okay, so this is the omega t value. So that is the time we are representing. Okay, it's the V and I both are in. So this thick line implies the voltage, and current line is with the dotted line. Okay, so here is the maximum points they are having the 90, 270, right? And so here is the, these are in the in phase there. So here is, you can say that is a, both are the voltage and current in the in phase with the each other. Okay, these are the waveforms. So here the vector representation. Okay, so if you are taking the resistor, so here reference, so take here the R. Okay, so voltage across resistor, so that is the, and current also in phase direction. Okay, so both are in phase with it. That's why it is the voltage current are in phase in the resistor that. Okay, for purest, but in the practically there will having the some values is different. Okay, so there will having the some variations in the practical resistor. Okay, so next we'll talk about the, so if power, so if you take the power in the resistor, and if the RL series, okay, so R and L, if the R and L circuit will be having, okay, so how it will be. Okay, so let's talk. So here is the instantaneous power. Okay, power we are having the three types of power. Okay, so remember, so we are having the three types of powers. Okay, so power we are having the three types. Okay, so that we also discuss in the next, but I will giving the three different. So that is the first is the active power, next reactive power, and apparent power. Okay, active power, reactive power, apparent power. Okay, so active power is nothing but which are indicating in the P. Okay, so reactive power which are indicate Q. Okay, so apparent power is nothing but S. Okay, so here apparent power S is equal to P plus Q. Okay, so active power plus reactive power get the actual power or apparent power. Okay, so here active power is equal to, that is a V into I. Okay, so we'll get the V into I, that is the, that is the apparent power. So here is active power getting the sine. Okay, so V I cos theta, V and sine phi. Okay, so that will be V I cos, okay, sorry, so here V I cos theta, okay, not sine, so V I cos theta, so Vi sin theta. Okay, so that is the theta. So here we will, that's the another part. Let's just then we are having active reactive powers. Okay, so apparent power, there are in the three types. So first we will talk about the instantaneous power. So for instantaneous power, here we are having the, so P is equal to Vi. Okay, so here we have taken the Vm sin omega t. Okay, so Im sin omega. So from that one get the Vm Im sin 2 omega t. Okay, so from that one we have taken the Vm Im of 1 minus 2. Okay, so sin 2 theta is equal to, that is the 1 minus cos 2 theta. Okay, so from that one we are taken Vm by 2 minus. Okay, so we have derived that. Okay, so next we'll take the first part. Okay, here having the, so 1 minus cos 2 theta. Okay, so from these equations we'll have getting the, one is the uh, constant value, another is the fluctuating. Okay, so real active power you can say. Okay, so one is the variable point and is the constant. So the fluctuate is nothing but there is a variable part, Vm cos 2. So that will be vary, so vary with the angle. So if angle is vary, the value will be also changes. So here is the depend upon the frequency. So that is the depend upon the frequency, the voltage and current will be changes. So here that we are by the whole cycle. So P is equal to Vm Im by 2. Okay. So that is variable point vector. So Vm by root 2, Im by root 2. So that will get the power is equal to P is equal to V into I. Okay, so where V and I are the RMS value. So V and I is the RMS value, that is the root mean square values of the voltage and current. So if the pure resistor, okay, So we can say that in a pure resistive circuit, the power, the whole cycle is never be the 0. Okay, so never be 0. Okay, that is about the pure resistive network. So that is a RL circuit, we can say that. So let's we talk about. So they're having the some problems we're having the uh, we're having. So given data is also given. We can go through the example problem. So that is a in AC circuit consider pure resistance of the 30 ohms and is connected across the AC supply, and 15 find the current and power. Okay, so find the current, power consumed and sinusoidal equation for the voltage and current. Okay, so here we are giving the so AC circuit is having so pure resistive and it will be supplied by the AC supply. Okay, so the voltage is the 220 volts 50 hertz and the ohms is having the 30 ohms. Okay, so we have to find out the current and voltage across the resistor. Okay, that we have to find. Okay, and power. Okay, we have to find it. So you can see the voltage, that's 30 ohms resistor, 30 ohm resistor, and voltage supplied and frequency. Okay, so current is equal to V by R. So current will have only one word resistance, that way V by R is equal to 220 by 30, that will get the 7 point. So power consumed, that is equal to V into I. So power in resistor will get the V into I. Okay, so V into I, that is the P is equal to V into I, that will calculate the to the V. Okay, so and I. Okay, so I into V, that's but we'll get the 1606. So VRMS, root mean square of the root mean square VRMS will equal to V is equal to 220. Okay, so whichever the value, so it's given in the practically, that's the RMS value. Okay, so if the average value, okay, so root 2 into, okay, so root 2 into VRMS will get the mean. Okay, that is will get the 311.0. Okay, similarly IM will get the amperes. So omega angle, okay, the angle omega 2 pi f. Okay, so we 2 pi f. Okay, from that one get the angle. So how much angle it will having. Okay, so equation Vm sin omega t. So we'll get the equation, that is the value. Okay, 314. So how much we are having the volts. Okay, so similarly Im sin omega t. Okay, so we have find out the omega. Okay, so from that one we substitute the values, we'll get that. So next we'll talk about the instantaneous power. Okay, so instantaneous power AC in a pure resistive circuit is always positive. Okay, you can see, so here we are having the E. Okay, so here is the and the voltage, and here is the current, the sum. Okay, so product V into I, that is always in the positive only. Okay, so never be in the negative direction. So you can observe, so this E is nothing but voltage. Okay, so I, the data line is referring the current. Okay, so instantaneous power, so always in the green light is showing, so that is the instantaneous power always in the positive direction only. Okay, that we have to, so they are only in the negative, only in the positive direction we get. So next we will talk about the inductor. Okay, so we have already discussed the inductor, and again we go to the some concept. So an inductor uses a coil of wire. So an inductor is a usual coil of a wire. So it is a coil of a wire. So you can see in the coil of wire, maybe in a rotational way or in the coil. So or it may it will be consumed to the one solenoid also in the hollow. Okay, so here inductor oppose the changes in the current through them by dropping the voltage directly proportional to the rate of change of the current. Okay, so here inductor oppose the changes. Okay, so inductor oppose the changes in the current. So inductor is oppose the changes in the current through them. Okay, by dropping the voltage directly proportional to the rate of change of current. Okay, so dropping the voltage directly proportional to the rate of change of current. Okay, so here if the current is increasing in magnitude, okay, if the current is increasing magnitude, the induced voltage will be pushed against in the electron flow. Okay, so if this direction, the opposite voltage in the reverse direction. Okay, so that's the difference. So next here, if current is decreasing, okay, suppose if the current is decreasing, the polarity will reverse. So the polarity will be reverse and push with the electron flow the opposite and decrease. Okay, so polarity will be changed in the variation in that. Okay, that we have now. So let's talk about the AC current through pure inductance. So if we have talk about the resistor, okay, now we'll talk about the how pure resistant, okay, so pure inductance with the AC circuit. Here we have taken the AC source and here in the pure inductor. Okay, so here the current is flowing, that's indicated with the I, and current through the inductor the IL. So I is equal to IL. Okay, so load voltage, that is the voltage across the inductor, that is RL, sorry, VL, that's indicating the terminal voltage ETVL. Okay, so here angle. Okay, so if you take the representation, vector representation, the angle is the voltage, applied voltage to the current, that is the lag. Okay, so in the lagging direction. Okay, so we can also represent this one is the, we can say here the voltage is there, the current is lagging here also. Okay, so it is having the 90 degrees to them. So suppose if the pure resistant, okay, so this is the pure resist, so if it is not pure, so it will having the angle which are having the some different. Okay, so in the inductor we can say that the current is lag behind the voltage. Okay, so current is lag behind the voltage, so it is the voltage is leading, so leading meaning what, so which angle is first. Okay, so here is the having the 90 degrees. Okay, so both are having the 90 degrees angle. So pure resistor having the 90 degrees angle. So if unpure, okay, so we're having the unpure inductor, the practical inductor having the less than, okay, so less than the 90 degrees, right? Okay, so next we'll talk about the relationship in the pure inductive circuit. So here you can see, so the relationship in the voltage drop across the inductor is the rate of change of current through the inductor. Okay, so E is equal to L di by dt. Okay, so you can also, there is a Faraday's law, okay, minus L di minus N d phi by dt. Okay, that's so similarly for here is the N is the constant. Okay, so from the L is the constant, from that one E is equal to drop E is equal to L di by, that is rate of change of current in the circuit will be varied, that's the L is equal to di by dt. So next we'll talk about the derivation. So voltage, supplied voltage, that is the Vm sin omega t. So drop occurs, that is a minus L di by, that is a which of opposing direction, that so induced voltage, that is the opposite, that's why we'll take the minus time. So from that one V is equal to minus I. Okay, so L di by dt. Okay, so Vm sin omega t is equal to LDL. So whichever appear, that is the same, it will go to the LDL. So from equating the both one, so we'll getting the di by dt. Okay, so from that one we're getting the integration on both sides, so we'll get the I is equal to Vm by L. Okay, so in integration of sin omega t dt, so we'll getting the Vm by L, so minus cos omega t by omega. Okay, so from that one Vm by L sin t, okay, omega t minus 5 by 2, so angle is the angle, that is our 90 degrees. Okay, so the angle, so in between that is our 90 degrees maximum. Okay, so from that we'll getting the, so here the value which you have to 1 at the maximum, that is will get in the only 90 degrees. Okay, so from that we'll get the Vm by omega L. Okay, so high is equal to Im sin omega t minus 1. Okay, so that we have get. So let's talk about the graphical representation. So always think that, so in the mathematical equation, so we have to do in the maximum value should be in there, there is no in the sine wave, sine theta, cos theta there. Okay, should be in there only in the values only. Okay, so if the I, so here we have find out the voltage, so from voltage current. Okay, so we have just take the how what should be there. Okay, so without having the sine and cos values. So here graphical representation of the voltage and current. So how it will be? So in the resistor we are talking about the both are, so in the graphical representation of resistor and inductor, so we'll take in the here is the voltage, and here is the current. Okay, this is for the resistor. Okay, so now we'll take the same similarly for the inductor, pure inductor, how it is there. So in the pure inductor, they are having some lagging. So here is the current and voltage will having the lagging behind that. That is 90 degrees lagging. We can see. Okay, you can see this is the maximum at points. Okay, so 90 degrees point will be having some lagging with them. Okay, so current slope is equal to 0. Okay, so voltage slope is equal to 0. That is a 90 degrees. Okay, the 0 it will having the maximum. You can see. Okay, so that will be different with that. So similarly we can draw. So if the voltage we'll talk about. Okay, so that is the variation. So voltage is there, then in between that there are values. Okay, so lagging, leading will be changes. So this is the current values. So lagging behind the voltage. Okay, first voltage will go, then current will become. That is the different. So this is the values you can see. So here is the voltage is flowing through this, then the current will become. Okay, that is the in the pure resistor net. So let's start the inductive. Okay, so here inductor. So if inductor indicating with the, here it is the inductor. Okay, so inductor will have indicating the L. Okay, so inductor also having the some resistance. Okay, so if the resistor is the resistance in the R. Okay, the units are the ohm. Similarly, every inductor. Okay, so every material having some resistance. So here the coil is made of the conductor, right? So the coil which is having the conductor. So that conductor having some resistance. So if the inductor, that resistance indicating with the XL. Okay, so that is called as the inductive reactance. Okay, that will indicate the inductive reactance. So here is the, it is the ratio of the magnitude the voltage and current. So it is the ratio of magnitudes of the, it is the ratio of the magnitude of the voltage and current. Okay, it is measured in the ohms. It is the measured in the ohms. Okay, Vm is equal to XL Im. So similarly for V is equal to IR, right? So here also V is equal to XL. Okay, so R is not but X. Okay, so A is the I. That is simple. Okay, so here XL is equal to 2 pi. So here from the inductance, so here whatever the inductance value is taken, so that from that will get the inductance. So here is the 2 pi FL. Okay, so that is the frequency concept. The frequency will be varies, the inductive nature also varies. Okay, for that the resistance value also varies. Okay, XL is equal to 2 pi FL. Okay, if you want to find the total reactant inductive reactance, from that one 2 pi FL, that we have to know about the what is the inductive. So that is the L value, so in henries. Okay, so henries. Okay, so that we have to take. Okay, so L value should we have to take, and F value, that's frequency we have to take. So self inductance, so we having the inductive, we having the self inductance, mutual inductance are there. Okay, so self inductance is that, so E later. Okay, L into I. So with the voltage appear to the across the inductor is due to the own magnetic field. Okay, that's the Faraday's one. Okay, that is the called as the self-in. Okay, so the current through the coil set up the magnetic field whose magnetic flux is proportional to the field strength. Okay, which is proportional to the current flowing through. So similarly, if the current flow, okay, then it is called as the self-in. Okay, so if the coil, okay, let's talk about. Uh, so if the coil, okay, the inducing that current is flowing. Okay, so similar the flux is producing. So due to the variation this flux, if the current is inducing, so that is called as self inductance. Okay, so next we'll talk about the power consumed in that. Okay, so if the power, so if we have taken the, for resistor we have taken the P is equal to VI. Okay, so similarly for L, so L resistor, so we are taking R is equal to P into I, that is the R. So now we'll take the L value. Okay, so for resistor we are taken, so for inductor power, what is the power equation? Okay, so here we are taken the instantaneous power P is equal to V into I. Okay, from that one. So here V is the, okay, so V is nothing but Vm sin omega t. I is equal to Im sin omega t minus. That is the angle. Okay, so that is the angle between, that is a 90 degrees variation. That's sin omega t minus 5 by 2. Okay, so from that one, minus Vm sin by 2. Okay, Vm Im by 2 sin omega 2 omega t. Okay, so the average power. So from that one, we have taken the average power consumed in the network circuit over the complete cycle. That's a one full cycle if we take in. Okay, we'll get 1 by 250 to 25. Okay, so full cycle. So minus Vm by that. So this is for the average. Okay, so for mean values you get, okay, Vm by 1, that one. So here the, if you take, so this is the power equations for the inductive nature. So here from, so similarly, so they're having the in the, okay, so here is the voltage and here is the current. So for resistor the power value, okay, so in the positive, but in the inductive circuit the power having the some lagging. Okay, so positive and the negative will be according to changes. Okay, so one thing remember, so there is no pure resistive network in the circuits. Okay, so practically every resistance, okay, so every conductor, okay, so every circuit having the some inductance nature. Okay, so there will have no pure inductive, so no pure resistive, so they having this some, every material having this some inductance nature. Okay, so next we'll having the negative, so it means that, so from this thing, so positive power negative power, positive negative. Okay, from this, so here the negative power, so in the positive that, okay, so it means that inductor is releasing the power. Okay, so here from negative power nothing but, it means the inductor is releasing the power back to the circuit. Okay, so inductor is releasing the power back to the circuit, well positive power means that is the absorbing. Okay, so positive power means then the absorbing the power from the circuit. Okay, so this is the one problem you can see. So AC circuit constant pure resistance 20 ohms and it is connected to the across the supply. Okay, so power, current and sinusoidal equation. So this is the problem, so we can alter. Okay, so we and today that is how it. Okay, so next you can see, next we'll talk about the pure capacitor circuit. Okay, so pure capacitor circuit will having the this one. So here we are having the capacitor, so in plate bits will take in there. Okay, so and here the angle, the I is equal to capacitor current. So here is the voltage. Okay, supplied voltage E is equal to Vc. Okay, that is the EC, we can say that. So here the angle, if you take the vector diagram, so this is the leading power. Okay, so current is lead before the voltage. Okay, so here current is lead because the capacitor stores the energy in the form of the charge. Okay, so capacitor store the energy in the form of charge. That's why current is lead in the capacitor. Okay, so we can also write this as the voltage. Okay, so I into V. Okay, so if we reversed, that is the different cases. Okay, so if the both, so here is the minus 90 degrees. Okay, so representation, so how we are representing, that is a different. Okay, so leading, lagging, so here we can say that this is the leading. Okay, so in this, that the current is leading the voltage, current is leading the voltage for. Okay, so resistor are in phase. Okay, remember, so in resistor voltage and current are the in phase, that is the voltage and here having the current. Okay, next here inductor. Okay, so in the inductor both the voltage, okay, so current is lag behind the voltage. Okay, so current is lag behind the voltage, so that's why we are taking the 90 degrees. Okay, here is the voltage and here is the current. Okay, so for here leading the voltage. Okay, so here we are having the minus 90 degrees. Okay, so current is leading, so current is leading in the capacitor network. So here the relationship we take, so that's in the relationship between the current through the capacitor, rate of change across the capacitor, that is the I is equal to C dV by dt. Okay. So we will take the explanation, that is the from the expression d by dv, the rate of change, that is the instantaneous voltage over the time per second. So capacitance is a farad. Okay, so instantaneous current will taken, that is the I. So capacitance is opposes. Okay, so the capacitor is opposed the changes in the voltage. Okay, so changes in the current, that is the inductor. So changes in the voltage, that is the capacitor. So changes in voltage by drawing the or supplying the current as they charge or discharge to the new voltage level. Okay, that is it. So here the flow of current, okay, the flow of electrons through the capacitor is directly proportional to the rate of change of voltage across it. Okay, so rate of change of voltage across the capacitor. Okay, so that we have taken from that one. So alternating voltage supplied across the circuit, the V is equal to Vm sin omega t. So always the supplied voltage is, that is a Vm sin omega t. Okay, so from that only the current will the Im sin omega t is the Im sin omega t minus cos t 5 by 2 plus pi by 2. Okay, that is it. So always the supplied voltage is the Vm sin omega t. Okay, remember. That is the RMS voltage we have taken. V is equal to 20 volts if taken. Okay, that is the RMS voltage. Okay, then the value, the charge on the capacitor in any instant. Okay, if we taken Q, charge Q is equal to C into V, capacitance into Vm sin omega t. Okay, so from that we'll get, so from that the current we have taken, so we'll get the value. So omega C Vm by omega t plus 5. Okay, so we'll get in the plus 5 by 2. Okay, so in the inductor we'll get in the minus 5. Okay, that is the difference. So from that one, Im is equal to Vm by 1 omega c. Okay, so here you can see the angle. So it's telling the voltage in the positive, the current in the negative. Okay, the voltage in the positive, the current in the negative direction. Remember, that is the current is leading behind the current. First the current is flowing, then the voltage is flowing. Okay, that's why the current value will be having the different. Okay, so here the in similarly in the here we are talking the, so that's value. Okay, so resistor, so in the resistor having the in phase. Okay, so inductor will having the lagging behind the voltage. Okay, so here is a leading behind the current. Okay, so leading behind the voltage, first the current is flowing here, you can see. Okay, after the voltage changes. So next we'll talk about the resistor. So in the, if the inductor having the resistor, that will talk at the X. Okay, similar the capacitance. Okay, so also having the some resistance that indicate with the XC. Okay, resistance in the capacitor that will indicate the XC. So XC is equal to 1 by 2 pi f. Okay, so 1 by 2 pi f into C, that is the XC by. So here capacitive reactance is the ratio to the magnitude of the voltage, magnitude of the current and capacitor. Okay, it is in the measured in the ohms. Okay, so not in farads. Okay, so it is measured in the ohms. Okay, so Xc is equal, so 1 by, okay, so 1 by, that is 1 by 2 pi Fc. Okay, okay, they will get, so that is the 1 by 2 pi Fc. So Sc is the capacitor in that. Okay, so units are the ohms. So remember, not in the ohm farads, so it is the units are the ohms. Okay, so resistors, all resistors value in the opposite direction, means that is in the ohms only. So the power consumed, the instantaneous power, so that's from Vm by 2 by sine 2 omega t. Okay, so average power, so that we have taken, so from that 1 by 2 pi 0 to 2 pi. Okay, that for a full one cycle that will get. Okay, 2 sine omega t d omega t is equal to 0. So that we have taken these one values only. Okay, so here can see power. Okay, similarly in the value, okay, in the capacitor also the power value having the positive to positive, negative, positive, negative. Okay, so here the power, so why it is, so here the power is called with the in the positive, that is the it will store the energy and release it. Okay, so if at the first charging it will store. Okay, after it will be discharged. That's why it will positive negative, positive negative will be flowing the power. Okay, so next we'll talk about the impedance component. So if the impedance, okay, so impedance is the defined as the ratio of the current to the volt. Okay, so voltage to current. So in the circuit, if the resistor, inductor, capacitor, so combining both will getting as a V into I. Now that is the impedance. Okay, so resistor, inductor, capacitor, combining both three is called as a impedance. Okay, so opposing force which is called as a impedance. Okay, so Z is equal to V by I. So you can see resistor, inductor and capacitor. Okay, so from that point we get the resistor. So that's the impedance value. Okay, students. So this is all about this. So impedance is also one of the opposing force in the circuit. So impedance values is nothing but the, so it is measured in the ohms. Okay, so impedance also measured in the ohms. Okay, so that we'll discuss in the next class, impedance. Okay.